Welcome back to my channel. This is Kusuma, studying in Sri Venkateshwara College of Engineering. Today we'll be discussing about Coulomb's law, its statement, vector form of the Coulomb's law, applications of the Coulomb's law, limitations of the Coulomb's law, and types of the charge distribution, that is line charge, volume charge, and surface charge. Let us start with the statement of the Coulomb's law. It states that the force of the attraction or the repulsion between the two electric point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between the two charges. The force acts along the line joining the two charges. Let us consider the two charges Q1 and Q2. The force acting along the Q1 charge is F12 and the force acting along the Q2 charge is F21. The distance between the two charges is R. Therefore, F12 is equal to F21 equals K into Q1 into Q2 by R square. Let Q1 and Q2 be the 2 point charges separated by distance R as shown in the figure in the medium which dielectric constant K. Then F proportional to Q1 into Q2, it is considered that as a equation 1, and F proportional to 1 by R square, consider it as a equation 2. From statement 1 and 2 we get F proportional to Q1 into Q2 by R square. So F equals to constant Q1 into Q2 by R square. The constant value is 1 by 4 pi K into epsilon naught into Q1 into Q2 by R square, where F equals force between the two charges. Epsilon naught equals to electric permittivity of the free space. Its value is 8.842 into 10 to the power of minus 12 Coulomb square per Newton per meter square or Farad per meter, where K equals dielectric constant of the medium. This expression is called a mathematical statement of the Coulomb's law. The value of the constant, that is 1 by 4 pi K into epsilon naught, equals 9 into 10 to the power of 9 Newton meter square per Coulomb square. Hence the equation of the Coulomb's law can be written as F equals 9 into 10 to the power of 9 into Q1 into Q2 by R square. In the CJ system, the value of the 1 by 4 pi K to epsilon naught equals to 1. Let us move on to the vector form of the Coulomb's law. So consider the two like charges, that is Q1 and Q2, present at a point E and B in a vacuum at a distance R. So let vector F12 be the force on the charge Q1 due to the charge Q2 and vector F21 be the force on the charge Q2 due to the charge Q1. So according to the Coulomb's law, the magnitude of the charge vector F12 equals vector F21 equals 1 by 4 pi K into 4 pi epsilon naught into Q1 into Q2 by R square. Consider it as a equation 1. Let R12 be a unit vector from a charge Q1 on Q2 and R21 be a unit vector from the charge Q2 on Q1. So as the force, vector F12 is along the direction of the unit vector, that is R21, and vector F12 equals 1 by 4 pi epsilon naught into Q1 into Q2 by R square into unit vector, that is R21. Consider it as the equation 2. Also force vector F21 is along the direction of the unit vector, that is R12. Therefore, vector F21 equals 1 by 4 pi epsilon naught into Q1 into Q2 by R square into unit vector R12. So therefore, R12 equals minus R21. Therefore, equation 2 becomes vector F equals 1 by 4 pi epsilon naught into Q1 into Q2 by R square into unit vector, that is R12. So therefore, from the equation 3, we can be rewritten as vector F12 equals minus vector F21. This is the vector form of the Coulomb's law. It is clear that it obeys the Newton's third law. A positive charge of the 6 into 10 to the power of minus 6 Coulomb is 0.040 meter from the second positive charge of the 4 into 10 to the power of minus 6 Coulomb. Calculate the force between the charges. This problem is based on the Coulomb's law. So as mentioned in the question, it is given that the two charges value, that is, let us take the value of the Q1 charge equals 6 into 10 to the power of minus 6 Coulomb and Q2 value is 4 into 10 to the power of minus 6 Coulomb. R value is 0.040 meter. So according to the Coulomb's law, we know that the formula F equals K into Q into Q2 by R square. So F equals 8.99 into 10 to the power of 9, that is the constant value, into charge value, that is Q1 and Q2 value. So 6 into 10 to the power of minus 6 into 4 into 10 to the power of minus 6 by 0.040 whole square. F equals 8.99 into 10 to the power of 9 into 2.4 into 10 to the power of minus 11 by 1.6 into 10 to the power of minus 3. Therefore, F equals 134.85 Newton. Let's move on to the applications and limitations of the Coulomb's law. Applications of the Coulomb's law is in order to calculate the distance and the force between the two charges. Coulomb's law also helps to calculate the electric field. Limitations of the Coulomb's law is the charged object must have a spherically symmetric distribution. Example, point charges or a charged metal sphere. The charges should not overlap. Example, they must be a distinct point charges. The charged body must be stationary with respect to the other body. Let us move on to the types of the charge distribution. First one is line charge. Line charge density. Line charge density refers to the amount of the electric charge per unit length along a line. In the other words, it describes how the electric charge is distributed along a one-dimensional path. Mathematically, it is denoted by the symbol lambda and is expressed in the units of the coulombs per meter. A line charge can produce an electric field that varies with the distance as that would be expected from an infinite line of the charges. So therefore, line charge density, that is lambda equals dq by dl. Volume charge. Volume charge density represents the distribution of the electric charge within a three-dimensional volume. It describes the amount of the charge per unit volume at any given point within the volume. Mathematically, it is denoted by the symbol rho and is measured in the units of the coulombs per cubic meter. In the context of the electromagnetic waves, volume charge density plays a significant role in understanding how the electric fields and the electric flux behave in the different materials and mediums. It is an essential concept in the study of the Maxwell's equations and the behavior of the electric fields in the dielectric materials. So therefore, volume charge density is given by rho equals dq by dV. And the last one is surface charge. Surface charge density refers to the distribution of the electric charge over a two-dimensional surface. It quantifies the amount of the charge per unit area on the surface. Mathematically, it is denoted by the symbol sigma and is expressed in the units coulombs per square meter. Surface charge density is crucial in understanding the behavior of the electric fields near surfaces, such as interface between the different materials or the surface of the conductors. It influences the electric field distribution and the behavior of the electromagnetic waves as they interact with the boundaries and interfaces. Surface charge density, that is sigma, equals dq by ds. Thank you for watching. If you like this video, please do like, share and subscribe to my channel.